Hey guys, Mr. Backwork here. In this video, we're going to look at substitution in definite integrals. Now we know that antiderivatives play an important role when we're evaluating a definite integral using the fundamental theorem of calculus. And because of that, so will substitution. Just like we saw with indefinite integrals, we can also do definite integrals by using substitution. But not only can we use substitution to help us with the antiderivative part, we can actually avoid the resubstitution part at the end by doing a little extra manipulation with our u substitution. So in this one, we're going to look at evaluating the definite integral going from 0 to pi over 3 of the tangent of x times the secant squared of x dx. And what we're going to do in here is we're going to let u equal the tangent of x. Now remember, when we're doing our substitution, we also have to get rid of the dx in there, so we're going to do the derivative of this u thing. So this will say du equals secant squared of x dx, and then we're going to solve that to get dx alone. So this will say dx equals du over the secant squared of x. And now we're going to do our substitution. So plug in u for the tangent of x. So that'll be u times, we'll have this secant squared of x, and then we're going to get rid of the dx, and we're going to replace it with du over the secant squared of x. Now we've still got that integral happening on the left-hand side, but here's where we're going to do a little bit extra with that u thing as we're looking at the upper and lower bounds of our integral. And what we're actually going to do is take these values, the upper and lower values, and we're going to plug them in to our u equation right here for the x. So if we look at u of 0, because that's the lower limit, then we're going to take the tangent of 0, and the tangent of 0 is just 0. So when we plugged in the lower limit, we got 0 as an answer. So we're actually going to replace that lower limit down here with that answer that we just got. But now we're also going to plug in the upper limit. So we're going to do u of pi over 3. So that's going to be the tangent of pi over 3. And the tangent of pi over 3 happens to be the square root of 3. So that's going to go in as our new upper limit value. Now there is some simplification that needs to happen in here before we can get ready to do the actual antiderivative. So I notice that we've got this secant squared right here, and we've got this divided by secant squared. So those are going to cancel each other out. So now we've got the integral from 0 to the square root of 3 of u du. And now we're ready to do the antiderivative, the integral. So this is going to be anti-power rule. There's really a first power on this u. So we're going to take that u, we're going to add 1 to the power, and then we're going to divide by that new power. Now because we're doing a definite integral, I'm not going to worry about putting the plus c on the end. Now when we did indefinite integrals, this was the part where we plugged in what we knew about u to get our x variable back in there. But because we did this substitution with our upper and lower limits as well, we don't have to resubstitute that tangent back in. We can actually just evaluate this antiderivative right here at our new upper and lower bounds. So first I'm going to plug in the square root of 3. So this will say the square root of 3 squared over 2. Well, if I square that square root of 3, that just turns into a regular 3 over 2. And then we subtract, we're going to plug in the lower bound. So it'll be 0 squared over 2. 0 squared is 0, divided by 2 is 0. So we get 3 halves minus 0, which is just 3 halves. So because we also manipulated the upper and lower bounds on our integral using our u substitution, we didn't have to actually plug that tangent back in. Now we could have plugged that tangent back in, but then we would have had to use the original upper and lower bounds as we're doing our evaluating. But doing the substitution with the u and also with the upper and lower bounds can make evaluating that definite integral a little bit easier. Now in this example, we're going to evaluate the definite integral going from 0 to 1 for x over x squared minus 4 dx. In here, we're going to let u equal that denominator, x squared minus 4. We're going to have to do the derivative of this. So we'll get du equals 2x dx. I'm going to solve that to get dx alone. So this will say dx equals du over 2x. Now I'm going to do my substitution. So in my integral, we're going to have x over u, and then we'll get rid of the dx and plug in the du over 2x. Now notice we've got this x on top and this x on bottom. Those are going to cancel each other out. So we end up getting 1 over u, and then we have du over 2 with our integral. Now before we go too far, I'm going to do my substitution with my upper and lower bounds on my integral so that I can get my new upper and lower bounds. So if I do u of 0, since that's the lower bound, then I have to take 0 squared minus 4, and 0 squared minus 4 is negative 4. So my new lower bound value is negative 4, but then I also have to plug in the upper value of 1, so u of 1 is going to be 1 squared minus 4. 1 squared is 1, minus 4 is negative 3, so our new upper limit is negative 3. Now before we get to the actual antiderivative, having this du over 2 really means there's a constant multiplier of a half in there. So I'm going to pull out the half, and then we've got our integral going from negative 4 to negative 3 of 1 over u du. Now we're ready to do the antiderivative. And when we do the antiderivative of 1 over u, then that turns into the natural log of the absolute value of u. But we've got that 1/2 multiplier in front. So 1/2 natural log of the absolute value of u is our antiderivative. Remember, we're not putting the plus c on the end because we're going to evaluate this at the upper and lower limits. So first, we're going to plug in that upper limit of negative 3. So 1/2 times the natural log of the absolute value of negative 3, but then subtract, plug in the lower limit, so then we've got 1/2 times the natural log of the absolute value of negative 4. Now we can clean this up a little bit. We can actually factor that 1/2 out of here, and then it's the natural log of the absolute value of negative 3 minus the natural log of the absolute value of negative 4. A little bit more cleanup work that we can do. We know that the absolute value of negative 3 is just 3, and we know that the absolute value of negative 4 is just 4, so we get the natural log of 3 minus the natural log of 4 inside of our parentheses. Now one more step of simplifying that we can do in here, we can actually condense this down. Because we have a natural log minus a natural log, we can condense that down using division. So we take the first thing divided by the second thing. So we get 1/2 times the natural log of 3/4. That's going to be it for this video. Thanks for watching.